This conference will now be recorded.
Hello everyone. So in this video we will discuss questions, that is previous year's question from the exam IIT JEE Advanced, and that is from the unit equilibrium. Here we have a first question. It is saying that on decreasing the pH from 7 to 2. So first initially there is pH 7, then it is decreased to 2. That means it is now more acidic. The solubility of a sparingly soluble salt Mx of a weak acid. So this is the acid, corresponding acid from which Mx is produced in presence of some base which is containing the metal M. And the solubility of this Mx sparingly soluble salt increased from 10 to the power minus 4 to 10 to the power minus 3 mole per liter. From this information, we have to find the pKa of the Hx. So see why the solubility increased. That is the first question. First of all, see Mx when it will be dissociated, that is at pH equal to 7, what is happening first. So this is the first step, how to solve this question. Part by part we will break the question, that is the solution. We will break it in different parts. So the first part, what you have to do, when pH is equal to 7, Mx, that is in equilibrium with the ion M plus and X minus. Now this X minus, when you will increase the pH, you will decrease the pH, that means you are basically making it more acidic. Now more acidic means what? There will be increase in the H plus ion, and increase in H plus ion means what? X minus will be combining with this H plus and it will make more Hx. So the equilibrium will be shifted from Mx side towards this side, because now this X minus is consumed by the increased acidity to form Hx. So that is the reason when you are decreasing the pH, that is you are increasing the acidity of the medium, Mx, its solubility will increase. But what is happening at pH 7? Suppose this is the dissociation. So the corresponding Ksp value for this Mx salt, that will be equal to solubility of these two. So S into S, which is the solubility, and suppose this is S square. And this is equation number 1. We will come back to this equation after finishing the other parts. So in the next part, that is when pH is equal to 2. This is the second part, number 2. So in this case, again we will write this Mx. It is in equilibrium with M plus and X minus, just like we have done it before. Sorry, plus X minus. Now this X minus, the new solubility, suppose it is S prime for these two, because now the solubility is different. This X minus in presence of acid, because we have decreased the pH. So now the acidity is high. It will make some Hx, right? So this S prime, which I have written in the previous equation, that is a solubility. Now this S prime, the same amount will be reacting with this H plus. Now what is the H plus concentration? H plus concentration, it is 10 to the power minus 2. Why? Because pH is 2. That means H plus concentration will be 10 to the power minus pH. pH is 2. So here H plus is present in excess. But as S prime is the solubility of X minus, the amount of Hx that will be produced, that is also S prime. Now for this equilibrium, we will write the Ka. Now Ka is the dissociation constant of acid. Suppose any acid Hx, it is dissociated to H plus and X minus. The corresponding dissociation constant is Ka. But this reaction is the opposite of dissociation, right? Because here the anion X minus and H plus combining together, it is making the acid Hx. So that is the reason now I will write it as 1 by Ka, and that is equal to the concentration of Hx divided by the concentration of X minus and also H plus. Now in place of Hx, we can write S prime. In place of H plus, we can write 10 to the power minus 2. But in place of X minus, we will not write S prime. Now why it is so? It will be clear. Let me do it first. So now what I will do, number 3, one more, that is the third part of the solution. I will write the Ksp for this new, that is at pH 2, I will write the Ksp for Mx. So that will be equal to S prime multiplied by the concentration of X minus. Now X minus I have not written S prime. This is because in the medium X minus which is produced in this equation, that is again in the second equation consumed by H plus. So its concentration is basically dependent on Ksp. So that is the reason X minus I am expressing it like this. Got it? So this is the third part. Now if this is third part, this value I will put here. So I will write it here, Ksp divided by S prime, but that I can write it like this. So this value I'm just putting it here, right? So this is the value of 1 by K, that is equal to S prime square divided by Ksp into 10 to the power minus 2. And suppose this is the second equation, but we can arrange this equation like this, that S prime square, that is equal to Ksp divided by Ka multiplied by 10 to the power minus 2. So this is the value of S prime square. And suppose this is equation number 2. So now we have equation number 1, we have equation number 2. S prime, another one is S square. So if we take, that is now we have reached the part 4 of this solution, and in this case what we will do, equation 1 divided by equation 2, what you will get, S square divided by S prime square, and that is equal to Ksp for S square, and for 1 by S prime square it will be Ka divided by Ksp into 10 to the power minus 2. So Ksp will be cancelled. Now you are left with Ka divided by 10 to the power minus 2. But these two values basically you know, because it is already mentioned solubility is changing from 10 to the power minus 4 to 10 to the power minus 3. So here I will write 10 to the power minus 8, which is the square of 10 to the power minus 4, and the square of 10 to the power minus 3 is minus 6, and that is equal to Ka divided by 10 to the power minus 2. Finally Ka will be equal to 10 to the power minus 8, 10 to the power minus 2, 10 to the power minus 6, and it will be equal to 10 to the power minus 4, right? So if it is so, pK value will be 4. So in this way, we have broken the solution in different parts. First part, you have to write the expression for S square. Second part, what is happening at pH 2, you have to write the expression for 1 by Ka, but when you will put the value of X minus square, X minus concentration, then put it in terms of Ksp, so that when you will finally take the ratio, Ksp will be cancelled from both sides. So pK is 4, that means correct option is option B. Okay. A solution is prepared by mixing 0.01 mole each of, here total 4 compounds are present: carbonic acid H2CO3, sodium bicarbonate, sodium carbonate, and sodium hydroxide. So everything is present 0.01 mole, and the volume is 100 ml water. You have to find pH of the resulting solution. Given pKa1, pKa2 for the acid H2CO3, because here 2 times dissociation is possible, so that is why 2 pK values are there. Okay, one is 6.37, which is the first pK, and the second pK is 10.32 respectively, and log 2 is also given. So what is happening here? Total 4 types of compounds are present, right? So in presence of these 4 types of compound, you have to understand what are those substances where reaction is possible. So here we have H2CO3 weak acid, and that can react with NaOH. So this reaction is possible, and that is expected because NaOH is base, so it will try to react with acid rather than reacting with NaHCO3. It will prefer to react with H2CO3 because the fast dissociation is better in case of H2CO3. And that is after H2CO3 fast dissociation, what you get? You get HCO3 minus, which is present in NaCO3. Now the second dissociation is difficult, so that is why you should write the reaction between NaOH and H2CO3, not between NaOH and NaHCO3. So this is the reaction we have written. Here the salt will be produced NaHCO3, and 1 mole of H2O. So you have taken both these 0.01. So initially it will be there will be nothing, but once reaction is complete, both will be 0 because it is 1:1 reaction, and this one will be produced 0.01, right? So if it is so, and that is this is the NaOH produced, but you already have this amount, so total amount will be 2 mole, which is present in 100 liter. Now finally in the medium, what you have, H2CO3 and NaOH both are completely consumed, so you do not have them. You just have NaHCO3 0.02, and you also have this Na2CO3 that is also present, 0.01 Na2CO3 and 0.02 NaHCO3. Now Na2CO3 is nothing but CO3 2 minus, and NaHCO3 is nothing but HCO3 minus. So HCO3 minus, if you consider as acid, weak acid, this is the corresponding conjugate base or salt. So finally in the medium you have the mixture of Na2CO3 and HCO3. So these two together will make buffer, isn't it? Now buffer of which acid? Buffer of HCO3 minus acid, because it will also act as acid, because, and you have to consider the second dissociation because the first H is already gone. Now when it is second dissociation and you have this buffer system, you have to find pH. That is the question. So you can take the help of Henderson-Hasselbalch equation. So pH, that will be equal to pKa, but which pK? We will take the second one because we are dealing with HCO3 minus, not H2CO3, plus log of the concentration of CO3, which is the conjugate base of salt, divided by HCO3. Now pK2 you already know, 10.32, and here concentration of CO3 is 0.02. Now if you are thinking that this is moles, this is not concentration, but see, you are just taking the ratio. So even if you divide the moles by the volume, the same in the denominator also you are dividing by volume, so ultimately it will be cancelled. So don't waste time in finding concentration, directly you can put the moles. So it is 1, and this one, that is HCO3, 0.02. So this ratio you will get 10.32 plus log half, but log half is basically like this. So it will be minus log 2. Log 2 value is given. So ultimately it will be, sorry, it is 2. 10.32 minus 0.3, and that will give you 10.02. So this should be your answer. That is the pH of the solution. Okay. Concentration of H2SO4 and Na2SO4. So H2SO4 sulfuric acid, and here we also have sodium sulfate. So we have a mixture of these two. In a solution is 1 molar. So concentration of H2SO4, this is 1 molar, this is also 1 molar. Sorry, it is not 1 molar, it is 1.8 10 to the power minus 2 respectively. So this is for H2SO4 concentration, this is for Na2SO4 concentration respectively. Next it is saying that molar solubility of lead sulfate in the same solution, it is given in this format, x into 10 to the power minus y. This is the scientific notation. You have to find the value of y. That means you have to find the value of the power of 10 to the power minus 1. Some other informations are also given, the Ksp value of lead sulfate because it is sparingly soluble, and for H2SO4 we know okay, the first dissociation is, it is fully a complete dissociation, so its value is very high, but the second one is 1.2 10 to the power minus 2. So here also we will solve this question part by part. So the first part that you have to do, you have to write how Na2SO4, we know that it is salt, there will be full dissociation and it will produce 2 sodium plus and 1 sulfate ion. Now initially it has concentration 1.8 into 10 to the power minus 2, and these two will be 0, but once the dissociation is complete, these two will be 2 into, I am writing it as 0.18 and this one is 0.018. So this should be the concentration. So this is the first part. Now in the second part, we know that H2SO4 phase dissociation is fully complete. That means if the concentration of H2SO4 is 1 molar, when it will dissociate to H plus and HSO4 minus, the concentration of HSO4 minus is also 1 molar because of this complete dissociation. So what we will do, we will take HSO4 minus and we will write the dissociation. So it will again dissociate to H plus and sulfate ion, right? Now this is having concentration 1 molar. This is also concentration 1 molar. And for SO4, this is 0.018, right? Now this is here one interesting thing you have to understand. Look at the right hand side. In the right hand side, the total concentration, if you compare with the left hand side, here it is 1, but in the right hand side it is high. So if you take the QC value, it will be basically higher than the Kc value. That is the normal equilibrium constant. If you consider, it is 0.012, right? But if you take QC value, it will be 1 into 0.018 divided by 1. So this is greater than Kc. That means this dissociation will not be happening, but instead the reverse reaction will occur. That is, you can understand that is more, these two combine together and it will form more HSO4 minus because of this QC greater than Kc. So that is the reason what we will write 0.018 SO4. Suppose minus X amount is reacting. So this is also minus X, but this will be 1 plus X. So it is opposite. Normally what we do in the left hand side, we do something minus X and then we write plus X in the right hand side. But here it is opposite because of this. Now once you have written it, sorry, not you can write it as Ka. Basically this Kc is Ka. That's it. So the expression for Ka2, that will be H plus concentration, which is 1 minus X. Then SO4 concentration, which is 0.018 minus X divided by 1 plus X. Now this X is very small, so that is why you can write it like this, 0.018, because this is almost equal to 1. This is almost also equal to 1. So ultimately the expression for Ka2, that will be 0.018 minus X. But Ka2, what is the value? 0.012, and that is equal to 0.018 minus X. So X is basically 0.006. So up to this point it is clear. So this is our second part. Now we will do the third part. Okay. Sorry, it is not yet complete. Once we know this X value, next what we have to do, we have to find the SO4 concentration. So SO4 concentration is 0.018 minus X. And now you know the value of X. So the SO4 will be 0.012. Now why we are calculating SO4? Because in the next step we will need this value of sulfate. Because molar solubility of PbSO4 is given in this format, you have to find the value of Y. So PbSO4, when it will dissociate sparingly soluble, then sulfate concentration will be needed. So in the third part, now PbSO4, it is dissociating to Pb2 plus, SO4 2 minus. So if we consider solubility, this will initially it is as it is 0. This is 0.012, but when we will consider the solubility for Pb2 plus, we have to consider if this is S, then it will be 0.012 multiplied by, sorry, not multiplied, it is plus. Now if we write the Ksp expression, Ksp is given 1.6 10 to the power minus, so it is solubility product. Here I have missed the power, it will be basically like this. Okay. Then solubility S into 0.012 plus S. Now S value is very small. So what we will do, the S square, that we can neglect. So ultimately you are getting this one. So S will be equal to 1.6 divided by 0.012 multiplied by 10 to the power minus 8. Okay. Now minus 2. If I write it in this format, 1.6 divided by 1.2. That is, I am putting this decimal to the right hand side. Then what will happen? It will be 10 to the power minus 8, but this will be 10 to the power minus 2. Right? Now, this part you can consider as if it is x. Okay. So 16 by 1.6 by 1.2, it will be something value 1 point something. So in scientific notation, we can express it like this. So why I have changed this 0.012 to 1.2 like this? It is because if you divide 1.6 by this expression, it will not be scientific notation. Scientific notation, the part before 10 to the power minus something, that is always like 1 point something in this way, or 2 point something. So before decimal it is 1. So that is the reason I have changed 0.012 to 1.2 into 10 to the power minus 2. So that this part you can consider as x, and from this part you will get 10 to the power minus 6, and that this 6 is actually our answer because we have to find this y. Okay. Next question we will, okay, it is the same question. A solution of 0.1 molar weak base B is titrated with 0.1 molar strong acid HA. So B we are reacting with HA, but which one is taken in burette? The volume of HA, that means acid is taken in burette. Okay. So you will have BH plus A minus. So here you can consider this picture. Strong acid is taken in HA, which is 0.1 molar, and weak base, which is also 0.1 molar, that is taken in the conical. So gradually the volume of acid is increasing because we are adding it dropwise from the burette. Now look at this graph. What is the pKb of the base that we have to find? And this is the reaction which is given. If you look at the picture carefully, at volume 6, V equal to 6 ml, reaction is basically complete, isn't it? Equivalence point is reached. But if it is so, then the half equivalence point, that should be V equal to 3 ml. Now when V is equal to 3 ml, that is this point, and the corresponding line, it is cutting here, and this value is basically around 11, right? So if at half equivalence point V equal to 3 ml, the pH value is 11. Now why we are talking about half equivalence point, that you have to understand. When it is half equivalence point, what is happening? Half of B is consumed and BH plus, that is half of B, is already converted to BH plus. And under this concentration, that is under this situation, half equivalence point, the concentration of BH plus, that will be equal to concentration of B, right? Now these two are present in the medium, that is the conjugate acid, corresponding conjugate acid of base. It is present in the medium. So these two mixture, you can consider it as if it is buffer mixture, that is weak base and its corresponding conjugate acid. Now for buffer mixture, we can write the expression like this. Weak base, so POH, that is equal to pKb plus log of BH plus. So why we are using this equation? Because ultimately you have to find pK. Now we know at half equivalence point pH is 11. That means pKb should be 14 minus 11. And log this ratio is 1. Okay. Now if this ratio is 1, sorry, it is pKb, pOH is 14 minus 11. And pKb we are trying to find. So this part you will get 0. So ultimately pKb we are getting 14 minus 11, it is 3. So here the answer key is given like this. That is, there is a range. Because why the range is given? When you are considering this 3 ml, you can say that it is not exactly 11 from the picture. If someone is assuming some another value close to 11, then the answer may vary a little bit. But here it is 3, which is within this range. So it is okay. So this is the answer of pKb. And why we have chosen half equivalence point? Because only at half equivalence point, you can use from the buffer concept, you can use this Henderson-Hasselbalch equation. That is the reason we have considered the half equivalence point. And that is why this graph is required. Without this graph, we cannot solve this. An acidified solution of 0.05 molar zinc 2 plus is saturated with 0.1 molar H2S. So Zn2 plus saturated with H2S. What is the minimum concentration of H plus in molarity bracket required to prevent the precipitation of ZnS? So when you have Zn2 plus ion and you are saturating it with H2S, that means ZnS formation is possible. But ZnS will be precipitated only when it is crossing the limit of its solubility product. Okay, so that is it is asking what is the minimum concentration of H plus that is required so that ZnS will be formed, but we will prevent the precipitation of Zn. So we have to add H plus in such a way so that it is not crossing the limit of Ksp, but still there is ZnS formation. So Ksp value is given and overall dissociation constant of H2S, because it will be dissociated 2 times. First H plus and Hs minus, and the second dissociation is H plus S2 minus. Only in the second dissociation you are getting this sulfide, which will be reacting with Zn2 plus. That means overall dissociation you have to consider, and the overall is actually given 10 to the minus 21 K1, K2, K net. So first we'll write the first part, ZnS. Its formation you have to consider, the corresponding Ksp value is given. So it will be dissociated as Zn2 plus and there will be S2 minus. So these two constant solubility we have to consider, and that is equal to Ksp. So S2 minus concentration we will find from the value of Ksp, which is 1.25 10 to the power minus 22 divided by zinc concentration, which is given. And this is equal to. So now we know the concentration of sulfide. Now what is the second part? Now in the second part, you have to consider the dissociation of H2S, which is 2H plus and sulfide ion. Now we know the K net. K net equal to H plus square sulfide ion divided by H2S. Now H plus we do not know, but S minus we have calculated from the previous equation, so we can put it. H2S concentration is 0.1. K net is given 10 to the power minus 21. So you can cancel it both sides. That will be equal to 0.1, 2.5 or 1 by 25. Okay. So if you remove this square, it will be 1 by 5. So this is your final answer. That is the minimum H plus concentration. Obviously, it is in molarity, which is 0.2. So first, from the KSP and with the help of Zn2 plus given concentration, we have calculated what is the sulfide ion concentration, which is just needed to reach the KSP. And if you put it in the dissociation of H2S, and if you put the Knet value, you will be getting the value of the H plus concentration, which is just required to prevent the precipitation. If it is more than that, this is a limit. If it is more than that, there will be precipitation. Okay. 5 ml 0.1 molar oxalic acid solution taken conical flask, and you are titrating it with NaOH. So you have taken NaOH in a burette, and gradually you are adding dropwise NaOH to the conical containing oxalic acid. And there is phenolphthalein indicator. We know whenever we acid NaOH, if there is excess of hydroxide and basic medium, then phenolphthalein will be generating the violet color. So the volume of NaOH required for the appearance of permanent faint peak. So when we do this type of titration, from the phenolphthalein indicator color, we understand what is the final point, when we should stop the titration process, when we should stop the addition of NaOH from the burette. And what is the condition? When there is permanent faint pink color. So what happens? First there is pink color generation, then you gradually it will be diminished. Then again generate when the first drop of NaOH will be, you will be putting in the conical, color will be generated, but it will be diminished. Then again you are putting in this way. One time will reach when there will be a persistent faint pink. That means you have added NaOH enough. It is now complete, and there is slight excess which we can neglect. And these values are tabulated because we have done total 5 times experiment. Now see why we do different, that is the same experiment we do several times, so that we can take the average value. Now exact average we will not take. What we will do, as this 9 is coming 3 times, so basically here you have to consider the volume of NaOH. You have to consider 9. Don't take the average, just take that value which you are getting maximum time. So this is 9, right? We have to find the concentration in molarity of the NaOH solution. So this is a simple question. You are doing some titration between acid and base. You know the concentration of acid. You know the volume of acid. You also know the volume of base. You just don't know the concentration of base, and that you have to find. So first you will write the equation to understand what is the mole ratio in which the acid is reacting with the base. So here you can see 2H plus replaceable is there. That means the relationship is 1:2, and this 2H will be converted to sodium salt, and there will be 2 moles of water. But this much information is enough. It is 1:2. It is reacting in this way. So when you have 5 ml of this acid, and if you are multiplying with its corresponding molarity, what you get? You get the millimole. So here it is 0.5 millimole. Similarly, NaOH concentration you do not know. Suppose the concentration is X, but volume you know. So this will be giving you 9x millimole. But here, as there is 1:2 relationship, so ultimately you have to multiply this 0.5, because for 0.5 millimole of CO2H, for 0.5 millimole of oxalic acid, basically 0.5 into 2 millimole, double times millimole of NaOH is required, and that is equal to 9x millimole. So X value from this we can calculate. So what we will be getting? It is basically 1/9. So this is our final answer. What is the concentration of NaOH in molarity? And the answer is, it is 0.11. Okay. So first we have to find the volume of NaOH that we will use for the calculation from this table. And the second part is you have to write the equation so that you can understand the mole ratio between this acid and base. Once you have understood it, you can find the amount of oxalic acid you have taken in terms of millimole, and that amount you have to double before you are writing this equation, and from this equation you can find the value concentration of NaOH. For the following reaction, the equilibrium constant Kc at 298 Kelvin, 1.6 into 10 to the power 17. So what is the reaction here? Iron 2 plus aqueous sulfide medium, it is producing FeS. And this FeS is solid. So when equal volume of 0.06 molar Fe2 plus and 0.2 molar sulfide. See, molarity is different, but you have taken equal volume of this solution. You are mixing it. The equilibrium concentration of this ion is found to be this one. This is the equilibrium concentration. And you have to just find the value of Y. So first we will write this equation again. Now see, as you have added equal volume of this will be reduced to 0.03, half will be. It will be reduced to half. So that is why now the molarity is 0.03. Similarly, for this one also, it will be reduced to half. So molarity is changed, right? Now here, one interesting thing is that this is present in lower amount. This is present in excess amount. So when there will be reaction, and remember there is equilibrium. This is limiting reagent. So there is equilibrium. So whatever is the amount of FeS, that you have to consider in terms of Fe2 plus. So we can assume as if there is full conversion. So all the Fe2 plus is consumed. That means 0.1 minus 0.03 is remaining amount of sulfide, and FeS is produced 0.03. But see, here though we have written it because we have to write the expression of these two, but actually Fe2 plus this is, though we have written as dash, that is 0, but it will be still present, and its value is very, very low, and that value actually we are trying to find out. So you can write it as x. So what we will do, when actually we will write the expression for Kc, which is 1.6 into 10 to the power 17, and that is equal to concentration of FeS divided by concentration of Fe2 plus is 2 minus. Now the first one is 1 because it is solid. Now Fe2 plus, though we have written it in this way, but it will still have some concentration, this very low. So you can write it, but when you will put the value of sulfide, you can write it like this, right? So in the equilibrium expression, don't write the FeS concentration, that will not be correct. 0.07 FeS, we will not write its concentration. So Fe2 plus, that will be equal to 1 divided by 1.6 10 to the power 17. Okay. Now 10 to the power 17, it will be upward. So finally you will get 8.93 10 to the power minus 17. So minus 17, it is matching. So this should be the value of Y. Okay. So this is our answer, 8.93. Dilution process. Now this will take some time because you have to find the H plus concentration 4 times. Dilution processes of different aqueous solutions with water are given in list 1, PQRS. The effects of dilution of the solutions on H plus. So all these solutions, basically we will do some dilution, and this dilution will change the value of H plus concentration, and that description is given in list 2. Degree of dissociation is alpha, and for the weak base and for the weak acid, which is very, very less than 1. So you can neglect it. Degree of hydrolysis of the salt, that is also very, very low. and H plus means the concentration of H plus. We have to match this. So look at the list one, the first P. What is saying? 10 ml 0.1 molar NaOH. So NaOH 10 into 0.1, that means it will be 1 millimole. There is also acetic acid, HOAC, 20 ml 0.1, that means it is 2 millimole. So it will produce NaOAC, which is the salt of this weak acid and strong base and water. So when the reaction will be complete, it will be completely consumed. Remaining amount is 1 millimole because 2 minus 1, and this is also 1 millimole. So finally in the medium you have this weak acid and you have the corresponding conjugate base OAC minus, that is a salt. So this is basically a buffer system. So initial volume is 20 and 10, 30 ml. Final volume is 60, but whatever it is, ultimately the concentration of these two will be same. And that is, you will take the ratio of its concentration. So in the final, the volume is 60 for HOAC as well as for NOAC. So when you will consider the Henderson-Hasselbalch equation, that is a buffer, so this dilution effect actually doesn't matter. So this pH, then pKa, and that is the ratio. It is basically buffer, and for buffer we know there is no significant change in H plus. Okay, so it will not change, that is the H plus will not change and that is given in 1. So P should be matching with 1, and that you can have in C or D. So P is 1. Now for the second one, 20 ml 0.1 molar NaOH and 20 ml 0.1 molar acetic acid. Again NaOH acetic acid, but the amount is different. Okay, so this is actually answer, but I will solve it in the next slide because this slide we do not have a space. Now we will do it for Q. Now here we have 2 millimole NaOH and 2 millimole HOAC. So full reaction will be there and you will get 2 millimole of NaOAC. Now this is the salt of weak acid and strong base. So when you have this type of combination, you can use the equation which we'll use here, and here dilution is 20 ml 20 ml 40 ml to 80 ml, that means double dilution, right? So which expression we will use for weak acid strong base type of salt, and for that salt the hydrolysis basically we are considering. So here the expression that you can consider, you can directly use this formula KWKA. Detailed derivation is not required. If you know this formula, that is enough. So this is the H plus expression. Now if we take H plus 2, that is after dilution, and H plus concentration 1 before dilution, that ratio will be, this C will be changing to C1 and C2, KWKA same. So ultimately here you will get C1 divided by C2, which is basically C1 divided by C2, and C1 concentration, if you, this is the concentration of the this weak acid. Okay, so concentration will be 2 because C1 it is 2 times concentration, 2 times high. So H plus it is basically now halved. So from this we can say it is matching with, let me check in list 2, the value of H plus changes to root 2 times, because H plus 2, that is root 2 times of H plus 1. So that is why we will choose Q is matching with 5. Now what about the next one? 20 ml 0.1 molar HCl, that means 2 millimole HCl, then 2 millimole NH4OH. So you will be getting 2 millimole of the salt. Now this salt hydrolysis, when we consider, it is basically strong acid weak base combination, And for this, we can use the expression just like the previous one. Now it is root over KW multiplied by C. And in this case, if you compare the H plus 2, that is the ratio, it will be C2 divided by C1, and that is equal to 1 by 2. Okay. So in this way, if H plus 2, it is basically root over 1 by root 2. So it is matching with 4. So R is matching with 4 and 1 is left, which is S. Now for S, it is 10 ml saturated solution of nickel hydroxide, which is in excess of solid nickel hydroxide. Now this is sparingly soluble salt. So saturated solution of nickel hydroxide you have taken in equilibrium with excess solid NiOH whole 2. You are diluting it to 20 ml, so double dilution. But in the bracket, it is mentioned that solid nickel hydroxide is still present. That means it will not affect the H plus. So this is also equal to 1. So S is also matching with 1. So P is 1, Q is 5, R is 4, S is also 1. This is the correct option. Okay. So we are ending the session here. Thank you for listening.